Okay. Hello, everybody, and welcome. My name is Eram Memiş Yazıcı. I'm a Senior Research Specialist for the Virginia Tech Transportation Institute. We appreciate you joining the latest safety webinar and improving methods to measure attentiveness through driver monitoring. You have all come into the meeting muted, and we would appreciate it if you stayed muted until the QA session. If you have any questions during the webinar, please type them in the chat box, and they will be addressed at the end. We will have the captions on for your convenience as well. At this time, I'd like to introduce the presenters. Eileen Herbers is a third-year PhD student at Virginia Tech in the Engineering Mechanics Department in the College of Engineering. She has been conducting research at the Virginia Tech Transportation Institute relating to crash prediction algorithms and crash simulations using naturalistic data for the entirety of her time at VTTI and within the Division of Vehicle Driver and System Safety. The development of these driver attention algorithms forms a substantial portion of her dissertation work. Next, we have Marty Miller, who is a research associate in the Division of Vehicle Driver and Safety System, where he splits his time between conducting human factors research for industrial proprietary projects for original equipment manufacturers and developing technologies to assist in the completion of such research. His areas of interest include advanced driver assistance systems, automated vehicles, CV2X, and convenience features. Marty's technological skills enable the development of novel research techniques and support fast, efficient data collecting and analysis. He has a passion for automotive safety research and applies his skills and expertise to tackling the unique and challenging problems in this space. And next we have Jacob Walters, who has served as a senior research specialist for the Division of Vehicle Driver and Safety Systems. Jakes has a vast array of research expertise in this field. During his tenure at VTTI, he has been involved in the development, execution, and completion of multiple public and proprietary projects. Now that the introductions are complete, I will now turn it over to the presenters, who can begin their presentations.
All right, thanks, Aaron. Yeah, so we're here to present today on our, oops, my sharing went away. Oh, Eileen just got kicked out of the meeting.
I'm letting them back in.
1 second. Here, I can share in the meantime. Or not, cannot, I guess. All right. Sorry, it seems like she got kicked out and it won't let me show my slides for some reason.
Is she unable to join back in?
She's typing, not sure. Here, I will. Her internet went out, so. All right. Can you see the slides?
Aaron? Yes. Yes. Yes.
Okay. Can you see just the slides?
Mm-hmm.
Okay, perfect. All right, sorry about that, everyone. Our collaborator, Eileen, it looks like her internet has went out, so we'll try to kind of get through this as best we can without her. So we're here to present about our UTC project, safety UTC project. on improving methods of driver attentiveness through driver monitoring. So we'll give a little bit of project background first. So the impetus behind this is the idea that distracted driving is a predominant issue in vehicle safety. There are approximately 3,142 lives in 2019 that were affected by distracted driving, meaning fatalities on the roadway that can be attributed to distracted driving. So obviously it's a big problem in the transportation space in general. And, through this project, we're hoping to devise some algorithms that can help identify that type of behavior so that you might be able to do something about it in the vehicle. So it's important to understand, what metrics can be used to determine when a driver is inattentive. So, what do you have available to you to make that determination? How often a driver is inattentive during one trip? So just, that's important to know. It's also interesting to look at, would driver inattention increase with more advanced vehicles like L2 and L3, with the idea that drivers are less hands-on, therefore they may feel more comfortable with kind of disengaging from the driving task. And then it's also important to understand, what's the most effective way we can reduce this driver distraction. So one way we can do this is through DMS systems, driver monitoring systems. These have the potential to detect and reduce driver inattention. These are generally systems, they're cameras that are in the vehicle used to look at the driver and determine where they're looking. And that gives you an idea of whether or not they're paying attention. So this is a quote from a Euro NCAP 2025 roadmap that describes what the purpose of the driver monitoring system might be. So it envisages an incentive for driver monitoring systems that effectively detect impaired and distracted driving and give appropriate warning and action and take effective action. So that's something that Euro NCAP is pushing. They're going to be moving this into their required testing by 2025 because they see it as an effective way to potentially mitigate driver distraction and inattention. All right, Eileen, if you want to take back over at this point.
Yeah, I can take over.
Kind of stumbling through it.
Sorry, everyone. My internet kicked me out as soon as it was starting. Thank you, Marty, for taking over. Sure. But yeah, if you go to the next slide. So this project used a privately funded naturalistic driving database, which was made available to support this study's research, including the driver monitoring system and other vehicle metrics. So individuals were recruited to use the equipped research vehicles in place of their personal vehicle, which makes it a naturalistic driving database. And we're able to collect DMS output, including glance location and other vehicle parameters, including speed, acceleration, steering wheel torque, throttle pressure, and brake pressure. And there were other metrics that were calculated or collected, but these were the ones that we used in our algorithms.
And so first, what we'll do is we'll talk a little bit about the DMS evaluation we did prior to the development of algorithms. So we wanted to look at the effectiveness of the driver monitoring system from the collected data we had available. And to do that, Jake is going to walk us through that.
Okay, so one of the things that we wanted to do to begin with was to identify some areas where maybe the DMS would provide unreliable output, especially given specific driving scenarios. So what we want to do is find those problem areas. So we tasked our data reduction lab to do some frame-by-frame analysis and some reduction on some of the DMS output that we had from that database that we were using for the study. It did go ahead and reduce around 600,000 plus frames for us. We didn't have a lot of stringent criteria around what those epochs were. It was more along the lines of making sure that the vehicle was in motion to ensure that there was some sort of driving behavior going on during that clip. So that was the reduction lab's job was to go ahead and take a look at all those things for us. And then from that, we started gleaning more information. Next slide, Marty. So as you can see, we have a confusion matrix over there on the right. What we found from that reduction was that the DMS was somewhat predictably strong when it came to drivers looking forward, because that was sort of the default expectation that a driver driving is looking forward. But it was less reliable distinguishing between glances that were driving related but were not forward versus potentially a distracted glance elsewhere within the vehicle or in the driving environment. So that became a bit of a line we wanted to take a look at and see how we could break that down and how we could get into some of those details.
Did you say this was a camera system that was doing this?
Yes.
The DMS?
Yes.
Okay, thank you. Sorry, I had to join late. Okay, so it was a camera system. Thank you very much.
Correct.
And Don, we will have a QA session at the end too, where you guys can ask questions to the presenters or type in the chat room as well.
Okay, thank you.
So any epics that were reviewed by the reduction lab that had high disagreement between the DMS output and the frame-by-frame analysis were reviewed manually. That was something that Eileen and myself handled. So of those disagreed upon epics, around 2/3 had some type of obstruction to the DMS camera. So whether that was the steering wheel position, perhaps they were angled such that the spokes from the steering wheel were obstructing the DMS that was mounted on top of the steering column. Hand placement, such as the driver resting their arm at the 12 o'clock position while they were driving, or seating position, which ended up being a lot less frequent, but still did have some impact. Maybe the driver was leaning forward or to the left or right, or was raised in the seat for a brief period of time, checking their mirrors or something. So that would always take the driver's face out of the DMS view. Of those, 1/3, there was no clear obstruction or reason for the disagreement that we could find. But about half of those, we did find that the driver was wearing glasses. Now that could have been sunglasses or corrective lenses, but we did notice that while we were going through and looking at these discrepancies. We also did want to take a look at some unknown events, so not necessarily miscategorization of where the glance was, but the DMS would return an unknown gaze location. So 200 of those events were reviewed to kind of see if we could find any consistencies about where those unknown classifications were coming from. One commonality that we did find was, again, driver's face being obscured due to, just some of those environmental factors that we talked about before, whether it was the driving posture or just, drinking container, something like that, where the driver was potentially looking forward, but there was just obstruction between the driver's face and the DMS field of view.
Yeah, this is important to understand because although we saw, lower accuracy than we were perhaps expecting, a lot of that can be explained away by the driver, the steering wheel being in the way of the driver's face, causing an inaccuracy, or them holding something to their face or obscuring their face in some way. So it's important to note.
Mm-hmm. So one of the things that we did before we began some of the algorithm development in earnest was some benchmark reviewing. So we wanted to establish some form of classification of different levels of distraction. That way, when it came to compare DMS output to varying algorithms that we'd have sort of a natural, organic understanding of what those would look like. So we wanted to do that through video review. We arrived at 4 classifications for 4 different levels of distraction of the drivers. So we had not distracted, slightly, moderately, and very distracted. We'll talk about how we classified those in a moment. We also did some calibration. Mostly Eileen and myself did this. So we would review events in parallel, but separately, and then come together and talk about how we found the distraction level during those events. And our calibrations were usually over 90% agreement So we felt pretty confident in our methodology when it came to assessing these distraction levels as we reduce them. And this again is to be used for the algorithm performance to have that benchmark to compare it to. So given the context of the driving scenario, the epoch that we were looking at, we did come up with some of these numbers. So if we look in the lower right, not distracted, this is how we classified it. The driver is clearly engaged in the driving task, characterized by glances off-road to locations relevant for safe driving. So this goes back to some of the disagreement we saw earlier, where there can be off-road glances that are applicable to a driving scenario, but current DMS algorithms that weren't necessarily recognizing that. We had slightly distracted, 157 of those events. The driver's looking around, often to the center console, something like that. Maybe they were, adjusting infotainment, HVAC controls, something like that. We also had moderately distracted, a fewer number of those at 73, where there were more extended glances off-road. This could involve things like cell phone use, digging around the center console, talking to a passenger, or something like that. Lastly, we have very distracted, had the fewest number of those, but the driver did have prolonged absence of forward glances, looking, perhaps they were texting and driving, engaging with their cell phone. Again, just not attentive during that 10-second window to the driving task at hand.
All right, next we'll talk a little bit about developing our actual algorithms for determining driver inattention. The first method we're going to talk about is buffer-based methods. Sorry, these are essentially methods where the driver's attention level builds as they look to certain locations, either distracted or driving related. So that means that if they're looking at attentive locations like on road, they become more and more attentive per the algorithm. Drivers that are looking at inattentive locations like the center stack, if they're looking at long periods of time towards the mirrors or into their lap or something like that, that would build up their buffer for inattentiveness. And then they would become essentially inattentive or attentive once certain thresholds are met. And those statuses get reset every once in a while. So for instance, if you look off-road for more than half a second, then your attention, if you were currently attentive, we would then mark you as no longer attentive, and then vice versa. If you're looking off-road for a while and then you look back on-road, your inattention would then become attentive, kind of like that. And Eileen's going to talk to us a little bit about the development for those.
Yeah, so as Marty stated, the algorithm calculations were that attention duration and inattention duration. So those two values were calculated using the glance location as well as speed, acceleration, and those other vehicle outputs. And so as the attention duration increased and it reached some threshold, then the inattention duration would be set to 0. And vice versa. So then the attention switch is whenever those attention durations reset to 0. So then we had a counter throughout the event. And so then those three values made up the driver attention status. So that would put it into the bin of not distracted, slightly, very, moderately, or very distracted. And you can go to the next slide. And so here's kind of an example of how the attention duration increases throughout an event. So we can see on the bottom is the time, and then on the left axis is the attention duration, and on the right is the glance locations. So any of the glance locations that correspond to something that's attentive are marked in green. So that's the forward road view. Anything that's more slightly inattentive, we go up that axis. So that's the rear view mirror, instrument cluster. And then as they get more severe in inattention, where the driver is looking off-road or at the lap or at the passenger footwell, that's when those are very inattentive glance locations, and they're marked in orange and red. And so as we see in this example, As the time increases, the driver is looking mostly forward, and so that attention duration, the dark black line, increases as they're looking forward. And then we start to see some more glances towards the left mirror and off-road. And so the attention duration is flat at those points. And then as the driver keeps looking off-road for a certain amount of time, that's when it resets down to 0. So now the attention duration has reset down to 0, and the driver has to gain this attention duration through forward glances and other attentive glances. So if we look at the next slide, this is the opposite value. So this is the inattention duration. So for this, the inattention duration increases for any of those inattentive glances. So we can see on the left mirror, where they're looking at the left mirror, it starts to increase. But then because they go back to the forward view for long enough, it resets down to 0. And then when we look, when the driver's looking off-road, it has a very steep increase in that inattention duration. But then again, they look forward for long enough where it will be reset to 0. And it continues through this cycle and is opposite of the attention duration. So then on the next slide, this shows the attention duration and inattention duration on the same scale. So as we can see, the attention duration is much higher than the inattention duration. So the inattention duration is on the bottom. It's that light gray line. And so we can see it doesn't have as much of an effect because the driver is generally attentive in this example. But we can see that as the inattention duration reaches a certain point, that's when that attention duration resets to 0. You can go to the next slide. And so I'm seeing some questions in the chat that are asking about this, but how do we determine those threshold values? How do we determine what values increase the attention duration and how much? So at each time point, these values were calculated within the algorithm. And there are certain points along this algorithm development where we can make those changes. So the first one is, how do we use a combination of these values to output that attention duration, inattention duration, and attention switch? We saw where when the driver's looking at the center stack, that's more severe than if they're looking at their rearview mirror. So how do we determine what that slope should be? So what weights do we use to add to the attention duration and inattention duration? And then another part is in between the algorithm calculation, so those values, and then how do we determine the driver attention status? So how do we determine the threshold that the attention duration must reach to reset the inattention duration? And then how do we use the values, these values throughout the epoch to assign to the driver attention status? And then we have the driver attention status set up from the algorithm, but how do we compare it to the benchmark assessment that we had in the beginning? So how do we compare what the algorithm output has versus what we say is the ground truth or what we use through video reduction? And so then we can compare different parts of each algorithm to see how different variables affect the algorithm output. So this shows how speed affects the accuracy. So the orange color, that's for events that were low speed or below 25 miles per hour. And the purple events are at higher speed, so above 25 miles per hour. So this is just a simple separation of speed between the events. And on the y-axis is that average mean squared error per category. So this is the error between our algorithm output and our benchmark assessment. So we can see the low speeds, or that orange, has generally a higher error in each category. And so then we were able to review the events and figure out maybe why the speed plays such an important role in that. And we noticed that at lower speeds, drivers are generally looking around more. So either there's more going on in the environment because they're driving in an urban environment, or there's more things to look at rather than at highway speeds or anything that's a little bit faster. Drivers are generally not looking around the car. So that's when we started to include other variables rather than just glance location. So we included speed and steering wheel torque, because we want to know if drivers are turning, then they're not necessarily looking directly at the forward roadway, they're instead looking off to the side, and things like that.
Yeah, and just to make it clear, so the mean toward error here is from our initial algorithm that only used the driver glance location to try and predict their attention level. So we were getting high error at low speeds because we weren't being very accurate, because at low speeds, like Eileen said, the driver's looking around a lot more. So we needed to really account for this in our algorithm to get anything that was remotely usable. It's a very, very important finding, we think.
Mm-hmm. Go to the next slide. I think this is you, Marty. If you can talk about more about how we optimize the algorithms.
Yes, so we did a number of kind of rounds of optimization manually. So you actually go through and you look at and see, okay, what types of thresholds, or what is the average attention duration or inattention duration for all of the slightly distracted, moderately, and very. And you can kind of come up with some heuristics to try and bend them based on the algorithm output that we have. However, this is very slow, and we wanted to explore using different weights for all of the glance locations that we had available to us. So for instance, if the driver's looking at the rearview mirror, you don't want to penalize them or call them as distracted, or you don't want to say that they're distracted very quickly if they're just looking at the rearview mirror, essentially, as opposed to if they're looking at the center console, right? Then you might want to say they're distracted more quickly. So this is very difficult to do manually. There are, I'm not sure how many billions this is, or trillions or quadrillions or whatever, but there are this many combinations given the parameters we had available in our algorithm. So we basically did a random search of our parameter space to officially determine the best set of parameters for that basically matched our benchmark events the best. So this got through a lot of the manual work and was able to automate a lot of this for us. We did 20,000 iterations of this. So we tested 20,000 combinations. That took several days of compute time to do. And yeah, more would be better, obviously, but we feel like this gave us a pretty decent set of parameters for what we were trying to accomplish. So that's how we got our final kind of buffer-based algorithm and the weights associated with that. In addition to that, we also explored some deep learning methods. So to officially incorporate other data sources like vehicle steering, brake, and throttle, this was a much better method to do that. Even with the kind of random parameter search, you still have to find some way to incorporate a new type of data. Like if you want to incorporate, well, okay, what if they're braking? Does that affect their level of attention or not? Or what if the amount of throttle they're putting in, does that affect it or predict it in some way? That's very difficult to do in the kind of buffer-based algorithms that we were initially exploring. So we used some deep neural networks. These use the same 10 seconds of data that was available in our benchmark events. So from our DMS data, we had one hot encoded glance locations. And then we had various vehicle parameters to assess the driver's attentiveness in addition to that. All of the vehicle parameters were normalized. So from -1 to 1, the values used in the network, or no, sorry, from 0 to 1, actually, because a lot of them were either off or fully on, like throttle or braking, for instance. And all the models we created and trained were using Keras in TensorFlow, and training data was taken directly from our benchmark assessments. Here is a look at the model we developed. This is actually based on some work that somebody else at VTTI did, Fong, on some not similar work, but he was using similar type of vehicle data, and it seemed like a decent fit for what we were using. Ultimately, this is definitely overkill for what the available data we had. We think that incorporating more data to our training set would really help increase the accuracy. but this was an exploratory kind of step to see what we could get out of it, and the results weren't that bad. So we'll speak to that in a little bit. Right now, Eileen.
Yeah, so another portion of assessing the algorithms is determining how accurate they are and how to determine how accurate they are. So we have the benchmark assessments where when we review the videos, we have the driver's attention status, and then how do we compare it to what our algorithm is giving. Go to the next slide.
Yep, sorry.
No, you're good. So the easiest way we had was using the average mean squared error. So for each category, the driver distraction level was given a value where not distracted is 0 and very distracted is 3. So then we're able to numerically determine the difference between our algorithm output and our benchmark assessment. And so the buffer-based algorithms are in orange, and then some of those machine learning algorithms were in purple. So we can see that the orange, or the buffer-based algorithms, were pretty consistent across each distraction level, whereas the machine learning algorithms were very accurate at the not distracted level. So it had the lowest average mean squared error, but then generally had higher error at these moderately and very distracted cases. And this is mostly because we didn't have enough cases of very distracted and moderately distracted events. And so the machine learning algorithms tend to bias towards the not distracted cases. So in general, they would describe most cases as not distracted, even when the driver was very distracted. And so then another way to compare our baseline assessment to the algorithm output is to determine the percent algorithm output that was exactly correct. So if the algorithm said that the driver was slightly distracted, where during our review we said not distracted, generally it's very close. So we don't want to say that it's entirely off. But if the algorithm says very distracted and we said not distracted, then obviously there's a big discrepancy. And so this percentage just shows the percent that is exactly correct. So we can see the machine learning algorithms. Let's see if you click through, Marty. Perfect, yeah. So those are very correct in the not distracted cases. But it looks like they're also a higher percentage that was exactly correct in the slightly, moderately, and very. So if you go to the next slide, it might be a little bit confusing, but essentially any dark red or dark orange, that's pretty bad. That means that it was very off. So although it had a higher percentage that was exactly correct, whenever it was incorrect, it was very incorrect for the machine learning algorithms. So it was off by more than one space. So the machine learning algorithms outputted not distracted when actually the driver was very distracted. So that can obviously present very dangerous situations. So this allows us to kind of look at the differences between the buffer-based algorithms and the machine learning algorithms more in depth, because it's giving how incorrect the algorithms are.
Which are the machine and which are the buffer based? I know I'm supposed to ask questions later, but I just got lost there and I needed help. I'm sorry, this is done.
Sure. So 0 through 6 are buffer based and 8 through 12 are the machine learning based.
Yeah, so anything on the left side of each graph. Yeah, sorry, it shows up earlier there.
Yeah, so.
Thank you.
Mm-hmm.
So overall, our performance, the buffer-based algorithms did outperform the deep neural network methods that we used, although we think that this is likely due to the amount of training data, as Eileen mentioned. So some of those models, though, do get a high number of exactly right. So they're kind of good at getting it exactly right, but then there's no necessarily like reasoning, there's no like logical flow to why they're saying that. So it's just like either it's correct or it's really, really wrong. And overall, that makes them less effective overall because they're getting a lot of cases very wrong, essentially. Yeah. So let's see. Yeah, I guess we can move on to conclusions.
Yep. Yeah. So in general, there are tools available now to make it possible to determine when a driver is inattentive. So having the driver monitoring systems and the other vehicle measures, we can determine when a driver is inattentive. But algorithms used to determine driver attention should be designed with an understanding of their limitations and can be used as a guideline for further development. So kind of like we showed, if you just have the glance locations, you really have to take into account the environment. Where we saw the speed really affects where the driver's looking. And we found through the algorithm development that at a minimum, both glance location and speed should be used to assess driver attention. But obviously including more variables can make it more accurate. And so overall, driver monitoring is an important component in detecting and reducing distractions. But just saying that we have these driver monitoring systems doesn't necessarily mean that we know when a driver is attentive or not immediately. So it takes a lot of analysis into what driver distraction really is.
Yeah, we were definitely surprised by the variation in kind of driver behavior based on speed alone. It really is very, very different. And if you're it's a very difficult thing to do because if the driver is looking out the left side of the car, it's very hard to determine if they're looking at a vehicle approaching and watching that, or if they're distracted by something. And it has a lot to do with how fast they're going. Obviously, if they're moving forward quite quickly, that isn't good regardless, probably, because they're not paying attention enough to the forward roadway. But it's very difficult with limited information available to make those assessments, especially in real time. One thing we kind of looked at initially, but weren't able to explore, was kind of the junctions or the roadway types. Those types of things would have been very helpful to understand. If they're in a parking lot, that's a very different driving environment than if they're in a, on a freeway. So it just makes a huge difference, and not being able to actually know where the driver is and what they should be paying attention to makes it really challenging. Something else we didn't explore, but we thought was interesting, was the kind of incorporating necessary glances around the environment. So requiring drivers to be looking around and not just looking forward as a kind of measure of being attentive. Because you can imagine drivers zoned out, looking forward, driving 70 on the highway. But if they're never checking their mirrors and they go to make a lane change, that's also a type of inattention, even if it's not as severe. So that's something we didn't get to incorporate here, but we thought was interesting and definitely worthy of kind of future work. I see we have a lot of questions in the chat. Aram, do you want to kind of work through these? Or do you want me to just kind of read through them?
The conclusions?
No, if you want, for the questions in the chat, we've got a bunch of questions.
Yes, I will go ahead and thank you everybody for the presentation. At this time, we welcome any questions. We do have a bunch of questions in the chat, so I'm going to go through. Okay, we had a question from Matt Camden. Can you provide additional information about the DMS used in this study? For example, number of cameras, placement, additional sensors, etc.
I think Luke did answer that in real time, but it was a single camera mounted on the steering column, and it did have IR emitters flanking that as well, just in case that wasn't clear.
And then we had another question by Mayud Islam. Just curious to know, how do you define very moderate and slight distraction, any threshold scale?
Yeah, so those those assessments are kind of our subjective understanding of the driver's level of distraction at that time or after the 10-second clip, essentially. We wanted to have a human understood version of what distraction looks like to compare our algorithm to, because it's very easy. When we first designed our algorithm, we did it without that. And essentially we said, okay, if driver's looking off road, the counter increases. And once it goes over 2 seconds, once they've been looking off road for more than 2 seconds, essentially, they will now be considered distracted. But looking at our data and looking at those low speed events, we noticed that that doesn't match our subjective understanding of what the attention level was. So we thought it would be better to have this kind of, it is subjective, but a more human understanding of what distraction looks like. And after reviewing all the events together, what distraction looks like, essentially. And then Jake and Eileen both reviewed those events, all the events, and came to an agreement on over a certain number of that they reviewed in parallel what kind of very moderate and slight distraction looked like. And it kind of, we tried to, and I can show the slide again, we tried to kind of stick to the guidelines here. So slightly was drivers looking around, sometimes to the center console for longer periods of time. Moderate was there had more extended glances off road than slightly distracted. Sometimes with phone use or longer use of the center console. And then very distracted was driver has combined sources of distraction with prolonged glances off road to a cell phone or to the center console. Hopefully that answers your question.
Thank you, Marty. We had another question by Gulis Tokatle. What is the threshold for certain time to evaluate inattentiveness?
Yes. So do you remember the exact threshold, Eileen, that we ended up with?
Well, we started with 2 seconds. That was the original algorithm, but eventually it changed because the attention duration didn't necessarily correspond to seconds specifically. Because like we said, any glances at the center console would be more inattentive than some other glances. So I think we ended at about 2.5 seconds, but it did change based on what values we used for, like the weights we used for those glances.
I'm looking it up real quick.
Okay.
If you want to do another question, I'll find it.
Yeah.
We had another question from Donald Fisher. Is this similar for visual distraction to what Katja Kircher used?
Let's see. So let's see. It looks like he asked later that looking at the rearview mirror is something that Kircher includes in her model. So 1 second does not decrease engagement. After that, engagement decreases linearly. Yeah, so we use a similar thought process where if you just look at the rearview mirror for 1 second, say, it could be distraction where the driver's not paying attention to the forward roadway and instead they're looking at something that's happening behind them. And so the 1 second isn't necessarily distraction immediately, but it increases that inattention duration. And so then once it combined with the other glance locations or other variables within the vehicle, then it could indicate distraction. So Kircher was included in the original algorithm development where it was just glance location. So then including those extra variables, that gives a little bit more insight into the environment.
Thanks, Haley.
Next question is by Matt Camden. Was driver fatigue included?
No, we did not. We were not looking at driver fatigue.
Thank you.
Although clearly still an important problem, but it was out of scope for what we were doing.
We have another question by Donald Fisher. Why does the attention duration keep increasing? Isn't there some maximum attention value? And he said, I may have missed it.
Eileen, I remember a graph where attention kept increasing. I can't get to it immediately, but I just didn't understand why it wasn't maxed out at some level since you could only play. Maybe I missed the entire point.
Yeah. So it's increased with those forward views and attentive glances. So if the driver keeps looking at the road, then it'll increase indefinitely. So once the clips we were looking at were 10 seconds long, so essentially it would eventually reach a threshold at the end of the clip. But once that inattention duration reaches some threshold level, then that's what resets that attention level down to 0, that attention duration.
So since attention can't literally keep increasing, would in the future you consider a threshold?
Yeah, so I guess the attention duration, it's not necessarily the attention level. It's just the duration of time that they've been looking at.
Thank you. So there might be a threshold independent of the attention duration. Got it. Yes. Okay, thank you very much.
Yeah, we weren't looking necessarily at this is when a driver is above a certain level of attention. We just like they're now currently paying attention. We're not gauging necessarily how engaged they are, or we're not assessing how engaged they actually are, because that's very tricky to do. Then you really need to look at probably more things to understand. Are they looking at the places they should? You probably need more information about what type of vehicles are around the car. Are there pedestrians they should be looking at that they are looking at? Those are things you'd have to incorporate into that kind of assessment. That said, this also resets after a short duration looking off road. So even if they're at 1 million attention duration, if they look off road for 0.5 seconds, it still drops off, right?
I got it. Yeah. So thank you. I understand what you did.
Perfect.
We have a question by Bernadette Phelan. Did you consider the geometry of the road by level of distraction?
We did not look at geometry of the road, no. We didn't have road geometry available. We could have, I guess, through our reduction and tried to include that. But we did not, not that I'm aware of. Eileen, we did kind of look at road geometry at one point. We thought about it, but it ultimately just didn't make sense for us, I think.
Yeah, I think that would be a great thing to include, but we didn't have that variable available for the entire data set. But what we tried to use to mimic that was the steering wheel torque along with their glance location. So if they were turning the wheel right and looking right and looking left, then hopefully that means that they're turning, and so they are still paying attention to the road.
Thank you. We have a question by Satyajit Upasani. They would like to know if an eye tracker was used, or if the glance locations determined by analyzing a video of the eyes, how were such precise gaze locations determined?
Sorry, can you repeat the question?
Yes. They wanted to know if an eye tracker was used, or if the glance locations determined by analyzing a video of the eyes, how were such precise gaze locations determined?
So the DMS is using eye tracking. How were such precise gaze locations determined? We were using a commercial system. So they give a location based on a world model that is developed. So you develop a kind of map of your cabin interior, and then it tries to predict where in that cabin interior they're looking based on their face and eyes. Yeah, so that's how such precise locations were able to be determined. And yeah, it was an eye tracking based DMS.
Thank you. We have another question by Donald Fisher next. Can you present the actual algorithm, the computer code or mathematical model, or is that not yet available?
Here I meant only the buffering model. I didn't mean the neural network.
Sure. It's not available yet. I think as part of UTC that we weren't planning to include that, but if there is sufficient interest, I think that we can make that available. We'd have to talk internally to see if that's if we're able to share it or not. But if we are able to share it, we're definitely happy to do so.
Thanks, Tim.
Christiana Ridgway said, I see that speed, steering, acceleration, etc. were all used to define driver attention as well as glance location, but it seems like only glance location was used for the graph you just showed. How were the others used to define attention? Yeah,
that's a good question. So so speed in particular, we actually used as a factor on the driver's inattention duration. So if the driver was going very, very slowly, their inattention duration would increase also slowly. The faster they went up to a certain speed, I think 35 miles per hour, then at that point, it would increase linearly with time. So this is a way to kind of get around calling slow-moving drivers that are looking around a lot inattentive when they're actually just kind of monitoring their environment appropriately. This is a way to get around that. For the steering, acceleration, things like that, for those we only use those in our neural network model. It's too difficult to try and hand tune cutoffs or heuristics for those things to incorporate them into the buffer-based model. We started doing it with like some things like steering early on, but it's very difficult to hand tune that for all the cases. It breaks down very quickly, and it's hard to capture all of the variations that we saw in the data, essentially.
Thank you. Next question is by Mueed Islam. When ML algorithm was applied, the sample size for very moderate and slight distraction, which is likely varied across the observations, was normalized with hot encoding or other process.
Yes, so we did essentially. So the output is a one hot encoded vector of assessment level. So each value means either slightly, moderately, or not distracted, slightly, moderately, or very. We did, while training the models, we weighted the training algorithm in Keras based on the sample size of each of our different classifications. So they were all weighted evenly to try and account for some of the imbalance in sample size.
Thank you. We have a question by Peter Burns. What's next in terms of applications?
Yeah, I think the next step is how do we use this information to reduce driver distraction? And so a big question is how do we notify drivers when they are being distracted? And it's a lot more complicated, I think, than we expected, because you don't want to notify drivers too much when they're not being distracted, because then it becomes a nuisance alert and they might turn it off, and eventually that becomes as effective as not having one at all. And so to be able to detect when a driver is being very distracted, notify them appropriately so that they can take the correct action and start looking at the forward roadway again, is a very complicated question, but I think is the next application.
Thank you, Eileen. We have another question by Donald Fisher. If you had a forward-looking camera, would that help supplement speed? Fast speed around a tight curve is not okay, but fast speed is okay on a highway. I'm guessing this is what you're saying right now, is what he asked.
Yeah, let's see.
Yeah,
so go ahead, Marty.
As I say, yeah, I think more information is obviously better. It is kind of a game of context, because if you're not understanding the full context of the driving situation, it's more difficult than we expected by far to determine driver inattention, or at least by using simple heuristic, like they're looking off road or looking at this location for so long. So the more information you can have, I think the better, and the better you're able to kind of make an accurate assessment based on the data available. Part of us, when we review the videos, we have that benefit as well, right? We can kind of incorporate that when we make our subjective assessment, which is why we chose to go that route, because we can make that subjective assessment, say, okay, yeah, they're on a 2-lane highway. they're looking off road a lot. That's clearly very distracted. Whereas if they're in a parking lot and they're trying to maneuver into a space or something, and they're kind of, looking back and forth, or, just kind of very, very slowly creeping forward, but kind of looking over, that's okay. That's not really distracted driving in the sense that we're looking at it. So yeah, I think, having more information is always better.
Yeah, do you know anyone who's now trying to incorporate these forward-looking analyses of the scenario into their distracted driving algorithms in order to reduce false alarms, or example of on the speed versus the parking lot? I don't. I'm curious whether you do know of any such attempts to incorporate the forward-looking algorithms, classifying the scenario ahead as one that really needs looking or doesn't need looking.
I'm not familiar with anything. Eileen, did you see anything in the literature?
No. Yeah, no one seems to have that forward camera that shows the environment yet. I think that would be very beneficial to include. But obviously it becomes more complicated.
Are you familiar with Katcher-Kircher's article on how important that is to these algorithms? It was a recent one in Human Factors.
No, so I'm not, but I've heard it was we used some of those processes in the original algorithm.
Yeah, she didn't add to the algorithm but she suggested that's the next step. Okay, I'll be quiet. Thanks. Great answer.
Thank you. We have a question by Carol Lau. Would supplementing additional cameras, doesn't have to be DMS cams, help identify what drivers may be looking at?
Yeah, I think that's what we were just discussing. So luckily this data set had those cameras available. So we could use our own subjective assessment of the driver attention based on the environment. So that was definitely helpful.
And we have another question by Donald Fisher. Can you display the buffering algorithm? If it is like Katcher-Kircher's, it should be fairly easy to display. Are you capturing cognitive distraction as Trent Victor does, and John Lee as well?
You've answered the first question. I don't think you've answered the second question.
Yeah, we weren't really looking for cognitive distraction either, because we weren't looking at dwell times or anything like that to try and predict that in any way. But yeah, that's a whole other can of worms when you're trying to understand, how actually in tune people are. We found this difficult enough, frankly. We had big plans initially. We certainly were thinking of all those things as the project went on, but we ran into enough issues, kind of just trying to get a very simple idea of 1 to 4, how distracted is the driver, and it's really difficult. We went into it very confident, but I think we still made good progress, but it's quite difficult problem.
I think you guys made great progress. Well, just because I'm asking these questions doesn't mean I didn't think you made great progress. Okay.
Sure. Yeah, that's fair. That's fair.
We have a question by Sao Mei Tan. Did you try to address look but now see problem, or is it out of the scope of the study?
So I guess she's trying to, or not sure, look but now see problem. So an idea of maybe you look but not see.
Yeah, look but not see. So if I look towards the right and there's a pedestrian there, do I really understand and predict what might happen?
Right. Let's see. No, we weren't really looking at, if they look but not see. So we weren't trying to measure if there was some kind of stimulus that they weren't responding to that they should be. This is another one of those things where we had designs, perhaps. We did at some point for all of our benchmark events get the count of cars and pedestrians and stuff in the environment using some neural network stuff, machine vision stuff. But we didn't incorporate that in any way. Like, for instance, if there were pedestrians there and they weren't looking at them, or if they were looking at them but they weren't making a maneuver that suggests they should have been. That's difficult as well. I mean, that's probably probably like finding a needle in a haystack, finding those events where people see things but aren't responding to it the way they should. We didn't really encounter that in any of the assessments that we made, as far as I'm aware.
Thank you. And I think that's the conclusion of our questions in the chat. We had one statement by Bernadette, feeling a good start and contribution to research literature. I would suggest to further develop the algorithm to include roadway characteristics and traffic conditions to proper put driver inattentiveness, driving distraction in context. Thank you for your presentation.
Thank you, Bernadette.
And if anyone else has questions at this time, please go ahead and unmute yourself and feel free to ask. I think Sam Tenyer, you will have to unmute. Let me see.
Okay.
Okay, we can hear you now.
Okay. I tried to write a chat, but I didn't know how to get it into the system. I'm kind of interested in what you see as a practical application of this research. I don't have any problem with what you're doing, but how do designers or people responsible for the roadway system are supposed to implement or use this, or how can they use it in their designs and development of roadway systems to make them safer? That's one part of it. The other part of it is in doing everything you did and try to identify distractions and things that aren't distractions, how does that affect workload? Did you think about workload applications or derivatives associated with this?
So in terms of driver workload, you mean?
Yes.
So we were not looking at cognitive distraction or driver workload as a focus for us. We were really just kind of can we predict drivers' visual manual distraction, essentially, in real time while they're driving. The obvious application is issuing some type of alert to say, okay, hey, you're distracted, you should be paying more attention. In terms of how this is applicable to roadway development or infrastructure development, that kind of thing, if you had this type of data, in real time while people were driving around and you knew what type of roadways they were on, you can maybe correlate it to understand, are there certain types of roadway features or something that cause more distraction, for instance, or correlated more with it.
Right.
And then you could maybe think about how you could devise systems where you either reduce the use of those roadway characteristics or features, or I'm not sure how. So, I mean, you could think of a good example as like intersections where people probably pull out their phone and look at it, right? We're not so focused on that because at low speed, there's no impact. There's no chance for them to hit anything. So we're really less worried about that. But yeah, I guess if there are environments where this type of thing is more encouraged or allowed, not encouraged, but prevalent, then it would be good to analyze that and understand, is there a certain type of environment where it's more common? Maybe there's something you can do, roadway signage to remind people to pay attention, or alerts in the car to tell them to pay attention, maybe that kind of thing.
The way I see what you've done, it's really you're assessing a tool for obtaining data, the relationship of the data, how the driver is using it relative to the infrastructure. So the next step is really, well, how can you deploy this technology to the betterment of the road design and road operations? That's where you should be focused. You can focus it on autonomous vehicles, I guess, but I think it's a broader picture than just that.
Yeah, it certainly is. Yeah. One of the big applications, and the DMS first came into use in the Cadillac CT6 with Super Cruise, because they wanted to make sure their drivers were paying attention when they were using a hands-off system. That's where it first came into use, but the application is far beyond that, right? I mean, Euro NCAP sees this whenever they're putting into in 2025, they're going to say, cars are going to be required to have something that predicts whether people are paying attention and alerts them if they're not, because they see it as as a big enough issue, right? They see the deaths happening every year, people being distracted and driving, and they're like, okay, we have a tool now, we can fight against that, we should use it.
I missed the first 2 or 3 minutes or so. What roadway system were you using? Rural two-lane roads, interstates? What was the
So this was taken from a naturalistic data set that was recorded I think all over Virginia. Any roadway type you can imagine we had in our data set for sure.
So is your data all mixed up in terms of your analysis? Yes.
We do actually have, for all the benchmark events, we do have we basically did the entire Sharp-2, if you're familiar with that, the Sharp-2 reduction for all the roadway characteristics, the lighting, weather, stuff like that. So we have all that data available for all of the events. We didn't present it today, but we do have that information.
That would be interesting to see.
Yeah.
Well, thank you.
Yeah, absolutely. Happy to answer the questions.
Anybody else has any questions, please feel free to unmute yourselves.
I see there's a question about using measures such as gaze entropy to evaluate driver distraction. I think this is similar to the kind of dwell times. We did think about doing that, kind of understanding. So if drivers are they need to be looking at certain locations for certain amounts of times, and that can affect their attentiveness. But we didn't look specifically into gaze entropy as it relates to driver distraction. I will read this article though. This looks really interesting. So thank you, Satayashit.
All right. If those are all the questions we have today, I would like to thank everyone again for joining the webinar. This webinar will be uploaded to our YouTube channel, and I will notify everyone via email when it is complete. Please feel free to browse our safety website to review the previous webinars as well. Thank you very much.